Yeah, I'm Dan Mitchell. I'm a professor here in Bristol, which is in the southwest of the UK. My expertise is climate science, and I do a lot more on Earth, let's say, than in other planets. But I have done a fair bit of work on Mars in particular and Titan. And so I'm going to give an overview of all planets in our solar system based on a review that I wrote with these people here. But just bear in mind when I start talking about things like polar vortices on Neptune, I suspect there are people in this room who have a far better grasp of that planet than I do. And so I'm part of the Cabot Institute, which is a environmental institute here at Bristol. I guess the first thing to mention is, entirely coincidentally, we've realized that in the southwest UK, which includes Bristol University and Exeter, we actually have substantial expertise now in planetary climate modeling and observations as well. And this was not by construction, but it does seem to be the case. So we've got my group at Bristol, Will Sevier's group, who was also at Bristol, now at Exeter. There's Jeff Vallis, who some of you will know, who's at Exeter. And there's Nathan Main, who does more exoplanets at Exeter. And so there's actually quite a critical mass here in the southwest now, and we are thinking of spinning up some larger projects and potentially doing some collaborative things. So if you're interested in that side of things, then please do get in touch. So just a little bit on my collaborators here. As I said, I'm more Earth-based than planetary-based. In writing a review on polar vortices in planetary atmospheres, we obviously wanted to cover a number of bases. We brought in, I guess Richard is more on the sort of fundamental numerical models. Likewise, Will. Nick Teamby here at Bristol is an expert in observations of planets, and Titan in particular is his thing. Stephen does a lot more of the gas planets, so we covered it there. And I guess Darren Wall's quite similar to me. He's at Baltimore, for you guys who know him. So we had published late last year a review paper in Reviews of Geophysics, and this was our polar vortices in planetary atmospheres. So we really felt that there was a gap here. There was a lot being spoken in the planetary community about new things seen on Jupiter, for instance, and trying to understand the dynamics of them. And we felt there was quite a lot that Earth's, say, vortex community had already done in that space, be it in a rotating annulus type experiment or in more numerical experiments. And so we felt a review paper sort of bringing the science together between the different communities was actually really needed. And so, yeah, this was published late last year. So I'll talk about that to give a bit of an overview. I'll then have a much more focused look at Mars, which is more of our specialty, I guess. And then I'll talk a little bit about where we're going next, especially in terms of exoplanets, with some of our collaborators there. Just to say that Emily Ball is my PhD student, and so a lot of this is her work, and I'll try and point that out when I can. So I guess the first thing is, like, how far can we go with this science now? You know, how good are our observations and our modeling? Clearly, there's a lot of work done on Earth because we live on Earth. We can use multiple sensor systems to really understand polar vortices in that space. But actually, we're at a really great intersection at the moment where the James Webb Space Telescope's been launched. We're starting to get the first images of that now. And one of the purposes of James Webb is really to understand exoplanets and their atmospheres more than we currently do. So it can see further, it can see in slightly different ranges. And we're not going to be able to observe, say, mountains on an exoplanet with this telescope. But what we should be able to do is get some really nice spectra out of various exoplanets. And so there's some great ideas of I guess combining modeling with those spectra. So if we see certain spectra, can we use our climate models to really interpret that? And we're really lucky in Bristol that we've got some targeted time on the James Webb Space Telescope through one of our lecturers, Hannah Wakeford. So she'll be looking at the TRAPPIST system amongst others. So that's a exoplanet system where we think there's a high chance of habitable worlds. So there's some really cool stuff we can do there. So what I'm saying is this is a really great chance to start thinking about polar vortices or jets beyond our solar system as well. And just to say, our climate models now are really, really quite impressive, and we can really model anything within reason, of course. And I just want to show this one animation of a world that we've modeled. So this is actually a fantasy world. It's not a real world, but of course this could be an exoplanet. This is some graphics we've developed at Bristol as well. So this is a planet from the Wheel of Time series. If any of you know that, it was an Amazon Prime series. But I guess my point here is, given certain conditions, in this case, land, ocean, some topography, and given a few things about the atmosphere, so assumptions made about the atmosphere in terms of its composition, the radius of the planet, etc., then we can actually make a very good approximation to what the dynamics are doing. And here you can see the red arrows. It might be very jerky, this, but if you go to the website down here, climatearchive.org, you can see this planet and you can see Earth and many things like that. But we can tell a lot about, say, the jet streams, the polar vortices and stuff using these climate models. So the combination of things like the Webb telescope and these new climate models, I think, is really exciting space for planetary atmospheres in general, and especially thinking about exoplanets. So my talk is mainly about polar vortices rather than jets, but they are very strongly linked, and I'll talk a little bit about the differences there and some confusion, I guess, between the communities. But this was one of the motivations for our review paper, was when we were talking about polar vortices, and we were talking with some people who do other planets, especially Jupiter, and we were talking about the Earth's polar vortex, and some of these people just weren't getting it, and they were like, oh, what do you mean? Oh, you mean these clusters of vortices we've seen at Jupiter's poles and things. And did we mean that? Actually, we weren't entirely sure. And then we started to think, what is a polar vortex? And there's no actual definition anywhere about what a polar vortex is. So we went about creating one. And just to say, following the review paper, I was interviewed by Simon Clark, who's one of these big YouTube influencers. And so you can watch our video on polar vortices there if you're interested. He's a very, very good video maker, by the way. So basically, what can we say a polar vortex is? Here's Earth, and this is looking down on the pole, on the South Pole in this case, and this is looking in ultraviolet. So what you're really seeing here is the ozone hole, and the ozone hole comes about because Earth's polar vortex in the southern hemisphere is so stable. The air remains very stable within that vortex, and ozone depleting substances can sort of get stuck in there, and the cold air reacts with that to create the ozone depletion. So there's what we would call a polar vortex on Earth. But if you were to look at Jupiter, and this is in the infrared, looking again down at the pole, that's a very, very different beast. There are 8 polar vortices surrounding a central polar vortex. So that's like a polar vortex cluster. So what is a polar vortex? Can you define it in a sort of physical way? Does it actually even matter? Do we need to define a polar vortex? Well, we felt that it was useful to define a polar vortex just because communities keep referring to these things as polar vortices. And actually, when you start reading papers, you can get very confused because certain people are calling jets polar vortices, others are meaning different parts of the atmosphere. So we thought a lot about it, and we thought, how would you define something like this? And essentially, we decided it was a coherent structure with absolute potential vorticity larger than the polar planetary potential vorticity. So just to break that apart and really explain what those terms mean, I'm going to be referring to this term potential vorticity quite a lot. Very confusingly, of course, it's also an acronym for polar vortex, but I'll only use it as potential vorticity here. So if you see it, then that's what it means. I won't go into detail about the maths behind that, but just to say potential vorticity is an amazing quantity in our atmosphere, which acts as a tracer. So we often use it to show where air masses go. It's essentially a measure of the local spin, but it can change because of the depth of the system. So as you see potential vorticity maps, just see it as a sort of strong vorticity area is the best way to think of it in the context of this. It increases towards the poles. So if we have potential vorticity that's stronger than the polar planetary PV, it's because there's something locally driving that circulation. And so that's what we sort of say is a polar vortex. We decided to sort of try and define this a little bit more in terms of things like Rossby deformation number and things like that. If you're aware of those things, I can discuss them more at the end. They're quite sort of detailed things, and I don't really want to discuss it because we decided they wouldn't be useful in the end. But so we've got quite a broad definition here, and we talk about type 1 polar vortices, which are mainly circumpolar flows. So Earth's stratosphere is very much like that, but we see these in other planets. And then type 2 flows, where we see smaller sort of asymmetries coming into place in vortex clusters here. So under this broad definition, it sort of describes the polar vortices we've observed in our system. So this is one of the most fun figures I've ever made in a paper, if I'm honest. And it was actually one of the easiest, of course, because it's a review paper. So I was just stealing pretty pictures from other people's papers in essence here. But what I'm showing is a snapshot of what the polar vortex looks like on all of our planets within the solar system, planetary bodies, should I say. So in the top, I've got the terrestrial planetary bodies, and in the bottom, I've got the gas ones. And most of these are looking down on the pole. So just to start with Venus here, Venus is a really interesting planet because we've visited it for longer and more frequently than any other planet. Yet this is sort of all we've got, which looks a bit embarrassing, actually, especially when you compare it with other ones. But that's because a lot of our missions to Venus have sort of been flyby missions, so very early on. And this is a snapshot image of Venus's polar vortex, so you can sort of see a swirling pattern going on here. This is a composite of multiple images, by the way, which is why you see these sort of breaks up in there. So that's Venus. A lot of the flybys don't go over the poles, they go over the equator, and that's why these images are actually quite hard to get hold of. And in fact, that's a repeating theme you'll see with most of these planets, is we have real problems viewing the polar regions, because in general, we only see the equatorial regions from our planet, at least. So Earth is very exceptional, of course, because we have so many observations of it. I've talked a little bit about this. This is a UV image showing ozone. So this, I guess, is a proxy for the stratospheric polar vortex in the southern hemisphere. In the northern hemisphere, there's less ozone depletion, although you do see a minimum there as well. We can look at other quantities, but that's the one we chose here. Mars is another particularly difficult one to look at. So again, I'm looking down on the pole here, on the northern pole. And this is during a large dust storm. I think it's in Martian year 26. If that means anything to you, great. If it doesn't, that's just just the 26th year, Martian year we've observed of Mars. And so you can see a sort of swirling pattern there again with the dust storm as well. It's not so clear, if I'm honest. And then Titan here, this is a cloud feature, extremely high resolution. Titan, by the way, if you're unfamiliar, is the largest moon of Saturn, and it has a very substantial atmosphere, so we can really look at the atmosphere there well. The nice thing about Titan and Saturn is we had a targeted space mission there, so it was the Cassini and Huygens mission, and so there's some amazing images of this particular planet, and when you compare them with some of the others, it's a little strange to sort of feel that this is I guess further away. But this is a great candidate for looking at some atmospheric dynamics, and here's a particularly impressive cloud feature. Jupiter is the sort of most impressive of the lot, because these were observed, I can't quite remember, 2017, something like that. And these were from the Juno mission sent there. And frankly, these caught, well, everyone, as far as I know, off guard. We weren't expecting to see these sort of vortex clusters at all, and incredibly impressive structures. They're quite transient, so we've only been observing them for sort of 4 or 5 years, but we have already seen vortices migrate inwards into this. All of these vortices on the edge rotate in their own way around the central vortex, but some migrate in and some migrate out. It's worth mentioning the other pole has got fewer polar vortices around it, and again we've seen migration. Well, that's the pole we've seen migration in mainly, I guess. So there's a lot of interesting structure going on there. Saturn, again, we've got a hell of a lot of detail. This hexagon is sort of a very well-known feature of Saturn and very iconic, I guess. A lot of people have referred to this as the polar vortex, but strictly speaking, that's not really true. This is the closest polar jet to the polar vortex, which is this central rotation here. And this is probably a standing Rossby wave or something causing this hexagonal feature. So Uranus and Neptune haven't experienced any dedicated missions, and so our images of them are, I guess, far lower resolution, and we're not concentrating on the poles. And so it's actually very hard to determine, is there a polar vortex on these planets? What does it look like? There are hints. We can sort of see a sort of lighter feature around the pole here in Neptune, for instance, potentially a cloud feature. These are infrared images, I believe. And again, there's sort of there are hints of banded structures, at least around Uranus poles here. But you would it's not surprising that people are sort of unconvinced by calling these sort of things polar vortices, let's say. So in this talk, I'll be really exploring just these terrestrial planets. We do explore all of these in the review, but I guess I'm not really an expert in the gas planets, and so I've left them out for this. So starting with a zonal mean view, here are the 4 terrestrial planets. We've actually got a hell of a lot of data for these planets now, and I was quite impressed to see some of these things coming out. So what we're using mainly here is a data set called reanalysis data. I'm not sure how many people know what reanalysis data is, but it's essentially where you take observations of a sort and you combine that with a very advanced forecast model to create like a global data set of that planet. So we use them a lot on Earth. We have around 10 different reanalysis data sets, and that gives us a gridded product of data, lots of different variables across the whole planet and out the depth as well. So on Earth, lots of observations go into this. So satellite observations, station-based observations, radiosondes, rocket sondes, all those sort of things. Of course, on these other planets, far fewer observational data sets go in them. So it might be as little as one satellite observation and a sounder or something like that. So what I'm saying is take these three, Venus, Mars, and Titan, with a pinch of salt. I wouldn't interpret small details on these plots, but I would hope that the large scale structures are there. So these are cross sections, and again, I'm using this quantity called potential vorticity. So the higher the number here, like the more spin in the system. And essentially, if it's dark red, you could think of that as the polar vortex. And what I'm doing is I'm looking at the altitude of the planet on the y-axis down to the surface versus the latitude of one of the hemispheres. And in general, it's the hemisphere relevant for the polar vortex. So that might be on Earth, for instance, this is the northern hemisphere winter, because that's the most relevant here. I could have picked the southern hemisphere winter as well. So I guess the first thing to mention is that there are strong potential vorticity blobs with very distinct vertical structures. Venus and Earth show this sort of maximum at the pole, which gets down to mid-latitudes in both of them. Mars is very different. It's showing a maximum away from the pole, certainly at this level, which is sort of 45 kilometers, something like that. And then potential vorticity drops off nearer the pole. So this is actually more like an annulus. And I'll show some visual images of that later to make it very clear. But there's clearly something strange going on here. You know, why a lot of fluid dynamicists would say this could be a very unstable system. And so we can talk about that a little bit. Titan's a little bit strange. It also has this annulus type structure. So large potential vorticity away from the pole. Just to say with Titan, because it's got such an extremely thick atmosphere, optically thick, it's like an organic haze, then we can't see below the stratosphere. So the troposphere, I just sort of scribbled out here to show that we don't really know what's going on there. So that's what a potential vorticity looks like. The thick solid lines here are the zonal winds. So you could think of that as the jet. And on Earth, we've got a stratospheric jet, which is the edge of the polar vortex. We've got a tropospheric jet as well, which I won't talk too much about. On Mars, we see this strong jet as well here on the edge. And then the jet sort of less of an obvious thing, I guess, on Venus and Titan here. So it's more of a gradient there. So there's a lot of data that's gone into these, but it's a good way just to compare, I guess, what the polar vortices look like on other planets. So I'll just look at each of these planets, one slide on each, just to explain the sort of interesting features of Venus. Many of these plots are in the review paper, but of course they originally come from a different source. So this is Garate Lopez in 2016, who was looking at Venus. So just to highlight again our polar plot of Venus, which is this one here, looking down on the pole, which is at the center. This is the wider polar vortex. This is sort of a composite over time. But if you were to look at individual flybys, and that's these three here, you could see much more transient features going on there. So this is temperature at the cloud top, I would say, the layer of the sort of where the clouds get up to. And you can see these particularly hot features on different flybys. So see, this is a snapshot in time for each of these three. There's a very transient wobbling around of the polar vortex. Some people have referred to it as a dipole. In reality, it's taken every shape under the sun, but it's clearly a chaotic feature. This is the vortex eye, so the polar vortex eye. And it's quite reminiscent of what we might see in a tropical cyclone on Earth, for instance, a lot of variability there. So there's been parallels drawn between those. So Venus has got this sort of very static polar vortex, which has stayed still for the entire time, but with a very chaotic central core there. Earth I won't dwell too much on Earth, but there are some interesting things. So this is, again, potential vorticity. I'm looking down on the pole in the Northern Hemisphere winter. So this is on the left-hand plot here is what we call a strong and stable polar vortex. If there wasn't much interesting dynamics going on, this would just be very symmetric around the pole. But we see this sort of elongation and a shifting off the pole. And that's from these upward propagating planetary waves called Rossby waves, which really shift the polar vortex off the pole, more so in the Northern Hemisphere because there's more land in the Northern Hemisphere and they really shift the polar vortex. So that's what the vortex normally looks like. But in extreme situations, it can break down, completely break down through dynamical processes. And these middle in the right plots show that. They show it breaking down because of a planetary wave of wave number 1, really depositing a lot of energy there. So it displaces off the pole and breaks down. Or it can split into 2 daughter vortices, and that's a planetary wave number 2 hitting it and depositing its energy. So why do we care? These are up in the stratosphere. Well, actually, they lead to really significant weather down at the surface. So this was an event called Beast from the East that I guess many of you in Europe and North America will be aware of because it sort of flattened all of our infrastructure. Really heavy snow events, very cold winter events, these breakdowns can be associated with. So it's not just a purely fluid dynamic problem we're interested in here. It actually has a lot of impacts at the surface as well. So this is actually what my group focuses on a lot. I'm flitting between planets here, so hopefully you're keeping up. But Titan is yet again a very different beast. So Titan being the main moon of Saturn, it has the same year as Saturn. So 1 Titan year is equal to 30 Earth years. So of course that presents a problem when looking at the evolution of the polar vortex. And the Cassini mission at the moment has been there for around 15 years. So it's observed around half of a Titan year. And these are sort of 3 different quantities very relevant to Titan, which also sort of have parallels with other planets as well. So on the x-axis here, I'm looking at the 15-year time span, or it's a bit longer than that, but around half a Titan year. And then I'm looking at the change in latitude on the y-axis. If you're familiar with looking at solar longitude, by the way, then that's the top axis. That's just a different way of measuring time on planets. So I'm looking around the core of the polar vortex here. So this altitude is sliced through the core. And this one here is the temperature of that core. So you can see in the Northern Hemisphere, the polar vortex is already very formed at the beginning of this time series. The dashed line shows the edge of that polar vortex. And you can see that it's much colder within the polar vortex region than the surrounding air mass. And that's again because the polar vortex edge really traps and makes the air very stable there. So we see that, and then we see the breakup and the decay of the Northern Hemisphere one, and we see the formation of the Southern Hemisphere polar vortex, where we actually see even much colder temperatures and more stable air within there. So it's nice that we're sort of managing to capture the full evolution of polar vortices, but not necessarily the same hemisphere here. Just to say, again, looking in potential vorticity, a similar sort of picture. Potential vorticity is negative in the opposite hemisphere, by the way. So if you looked at the magnitude of this, you're seeing very strong potential vorticity values in the polar vortex region in the Northern Hemisphere, and then very strong vorticity values in the Southern Hemisphere as well, just of the opposite sign. So that's sort of consistent. But I guess one of the real important things of polar vortices is their ability to trap chemical species. And so this is a problem on Earth because of the ozone, trapping of the ozone depleting substances and things. But on Titan, let's not worry too much about what this quantity is. It's a short-lived chemical tracer. A lot of the formation of the atmosphere of Titan can go on in the polar regions in the very stable cold air masses there, and then in some senses it filters out into the rest of the atmosphere as well. But there's yeah, it's sort of like a factory for a composition in some sense there, and that happens more on Titan than on many other planets, I think we'd argue here. Yeah, so that's Titan. Again, you know, take some of this data with a pinch of salt. So that was a sort of whistle-stop tour of the different planets. I'm just going to spend the last 15 minutes looking at Mars in particular, and I'm going to try and tease out this annulus shape that we spoke about on Mars. So this is a paper that I published 6 or 7 years ago. I did this while at Oxford, so this was with Peter Reed there, who's a fluid dynamicist there. We're looking at the two hemispheres of Mars here, and we're just looking at a composite of the polar vortex. So this is again a potential vorticity quantity. I wouldn't worry too much about the units. They can get very confusing and frustrating, and are often scaled in different ways. But again, the more red the color, the higher the vorticity, I would say, is the best way of thinking about it. And so here we can see a very distinct annulus shaped polar vortex. So stronger potential vorticity off the pole, and then going to zero or going to much less close to the pole, certainly not zero actually. It's less distinct in the southern hemisphere, but you still get a sense that there's some sort of annular shape going on there. I guess it's worth mentioning again that this is reanalysis data. It's not pure observations, and if something is going wrong in the underlying model of that data, it may well be that these features are not as clear or distinct as reality. So we think, we've done a lot of analysis of this. We think this annular shape is very true on Mars, but the degree to annularity is not necessarily known so much. The oval shape, by the way, is again from a sort of persistent planetary wave forcing from below. So that's why it's not entirely symmetric there. Just as a comparison with Earth, this is sort of a similar thing, but again, you see this this uniform increase from the center of the polar vortex out. So the strongest potential vorticity is in the center of the vortex, and then it gets less going out. And this is normally what you'd associate with a stable polar vortex. On Mars, this is very unstable. In its own system, it would probably just break down. So there must be a restoring force. There must be something causing this to be annular. And our work over the last 3 or 4 years has really been isolating what that would be. So this is the overturning circulation on Mars. It's something called the transformed Eulerian mean circulation. If you're unaware of that, I won't go into the details, but think of it as like a Lagrangian circulation. So you could follow the air mass. You know, if you were an air mass here, you would sort of go around in a clockwise direction in the red, and counterclockwise in the blue here. So this is a huge Hadley circulation going from one hemisphere to the pole of the other on Mars. Yeah, so this is the depth. This is the depth of Mars's atmosphere, and it's essentially the Hadley circulation on Mars. The descending branch of this is the polar vortex edge, and they're very closely linked, the Hadley circulation and the polar vortex edge. So there's definitely a key there as to what's going on. It's worth mentioning, if you were to look at the same quantity on Earth, and just as a warning, this is just the stratosphere of Earth. So the troposphere would be further down. You actually see extremely similar circulation. This is called the Brewer-Dobson circulation on Earth, so it's well documented. But just to say, there's some strong parallels here. So the fact that both have got polar vortices, there may be a strong link there. And I just want to do a shout out at this point to Professor David Andrews, who was a pioneer in transformed Eulerian mean diagnostics. Many of you dynamicists will know him, and many of you will know that unfortunately he passed away 2 months ago from an unexpected illness. He was really groundbreaking in this area. And when I first moved to Oxford, actually, I lent on him to understand these transformed Eulerian mean diagnostics. And this figure in particular, I discussed a lot with him. So I'd encourage you to check out his books as well, if you want to know more on this. So there's something to do with the Hadley circulation. What are the other forcings on Mars which could be important here? Well, we know dust is a really important feature of Mars. They have these global dust storms which encircle the entire planet. And so we wanted to look at how the polar vortex responded in those dust storms. And this is a set of images, again, looking down on the northern hemisphere polar vortex, again, looking at potential vorticity. But these are snapshots in time. So you could consider these as like a different Martian day, set 2 Martian days apart or something like that. And this is during a major global dust storm in Martian year 26. And what you can see is when the dust storm kicks in, which is around panels C and D, the potential vorticity in the polar vortex in general really starts to respond strongly. It gets much weaker, it gets much more destroyed. It looks like it's a very radiative type change, but we see some significant changes in there. So we're very sure that dust plays an important role in the polar vortex evolution and dynamics. So that was a paper, that was my 2015 paper, but Emily, my PhD student, has expanded on this and looked at some other years. Martian year 28 was also a really significant dust storm year. And I apologize that the color scales are different here, but I guess it's the structure I'm interested in, not really the values. You can see in Martian year 28, this is an average of that winter. The polar vortex was again very, very broken down, not really apparent there. And so there's definitely a key there. If you look at a composite of the 3-4 years following that event, you can see this strong annulus appear again, and that's very much what we expect it to be. So we're very confident dust plays a role. So combining that overturning circulation, the transformed Eulerian mean circulation with the dust, we see a really stark difference, actually. Again, this is from Emily's paper, and I encourage you to check it out. Again, we're using this reanalysis, so a pseudo observations. If you look at just the dust year, you see a really strong Hadley cell, a really strong overturning circulation. So here again, I'm just looking in one hemisphere, the northern hemisphere. If we looked at non-dust years, which is this panel B, you see that evolution is much weaker. And so the difference here makes that quite clear. And actually, the Hadley circulation is around twice as strong in the global dust storm year than it is in non-years. So it's really having an effect on the entire circulation of the planet. So it's not a surprise that the polar vortex is something that really stands out there. So what we really want to do is understand those differences, and the way we can do that is use sort of comprehensive global circulation models. I'll talk a little bit about the model in a second, but just to say this mythical model that we've used, how well does it reproduce these plots? Actually really well. We've modeled a dust storm in that year, and there we see this overturning circulation, and we've modeled non-dust storm years, and that's what we see here. And again, the difference is very stark, very similar to what we see in reanalysis or observations. So this is really actually quite nice, and it was a bit of a surprise to me that our models could capture this sort of change in dynamics so well. So that's quite nice. But let's talk just a little bit about what this model is. I'm not going to go into too much detail here because I've only got a couple more slides, and I want to get to the science. But we use a global circulation model framework called ISCA. This is based on the GFDL climate model, but it's been really sort of expanded and pushed hard by Stephen Thompson and Jeff Vallis at Exeter University. And so they've created a really nice framework of climate models. And it goes anywhere from a held Suarez type model, which is where you relax the climate to say a surface temperature profile, all the way through to a comprehensive global circulation model, which includes things like radiation schemes, very simple land schemes and things like that. The way to think of ISCA is our latest climate models, but 20 years ago. So they're you wouldn't use them for Earth's climate change, for instance, because they'd be too focused on a specific problem. The real power of ISCA is that it's very flexible to changes. We care about the large scale dynamics. We don't care about the local, say, extremes over a certain longitude and latitude. So it's ideal for these experiments of dynamics and using them in a wider context. So we've used ISCA to really figure out what causes this annular polar vortex on Mars, and that was the crux of the paper by Emily. And so we did a set of 5 attribution experiments. The great thing about climate models is you can switch on things that you think matter, or you can switch them off. And so what we did is a control experiment, which is just a bare bones. Think of it as like an empty climate model. So it has, the equations of motion in there and stuff, but it doesn't have anything forcing the model to do anything strange. We then introduced topography. So we said, here's the surface of Mars. How does that change the dynamics? We then introduced latent heat. There's some previous analysis saying that latent heat is very important for the circulation on Mars. So we created a forcing of latent heat. And then we introduced dust as well, which I showed before, we feel is important. And again, I'm sorry that the color schemes are slightly different here, but it's the structure I'm interested in. Starting on the left plot here, you can see that our bare bones climate model was really quite a symmetric model. Looking down on the pole here, you couldn't see much structure in the polar vortex at all. Once we added topography, instantly you started seeing a little bit more structure. When we did an experiment with topography and latent heat, we started seeing a little bit more structure again. And it was only really when we started including the dust and the topography that we started seeing something a lot more like what we were expecting. But actually, when we included everything, we started really reproducing this annulus in the polar vortex. And so that was quite exciting. It's like we used the sort of basic physics to understand what was going on, and then we sort of proved it in a climate model. And this was the first time, I would say, the sort of attribution of the annulus has been explored for Mars in this way. But there is some great work that was done before on, say, just the latent heat or just the dust parts and things like that. So work out of Johns Hopkins, for instance, has shown some of that as well. I guess it's worth mentioning the numbers are hard to compare, but if you want to, you can multiply this one by 10 and you're on the same scale. It's still not as strong an annulus on this model polar vortex in what we observe. So there might still be some missing processes there. We're not sure, but we're also not 100% sure how strong the observed annulus really should be. So we're just happy they're looking very similar, I guess is the point there. I'm just this is my final slide, and just to think that, we are thinking beyond our solar system now, and our final figure of the review paper was actually just asking the question, can exoplanets have polar vortices? Clearly, we can't observe these things, so we don't know yet. And so we did just model a planet, in this case, TRAPPIST-1e. So that's a planet around sort of 40 light years away. Nathan Main's group had sort of modeled this planet specifically. So we just took their data and looked at the polar regions, and lo and behold, we did find a polar vortex. That's definitely not always the case. If a planet's close enough to its star, it may have more radial flow, and that completely disrupt, and so polar vortices don't form in those cases. But in this case, it was far enough away from the planet that it did cause a polar vortex. And this is sort of a way forward, what we're really interested in exploring going forward. So yeah, next steps for us, and this is an artist impression of a brown dwarf, actually. So you can see the jet structures on here. Next step for us is we are looking a lot more at the exoplanet stuff. If you guys watched Yohai Caspi's talk, it was a couple of seminars before this one. Unfortunately, I missed it, but he's done a lot of amazing work on parameter sweep experiments. And so we're sort of jumping on that bandwagon, I would say. And we're looking very specifically at brown dwarfs, and so how you can do parameter sweeps there, and how you can link that with observations that we will get from, say, James Webb telescope. So I'm really excited about that, which is work done by my postdoc Mark Hammond, who's just moved to Oxford on a fellowship. So get in contact there. And then with Emily, her next stage in her PhD is really looking at, again, these parameter sweeps of zonal jets in Earth-like planets. So we're looking at using the ISCA model to really look at the span of, say, different radii or different rotation rates on planets. Yeah, so that's it. Here are the three main papers I spoke about. And yeah, any questions?
Great, super. Thanks so much, Dan. We have time for some questions. Feel free to, you can just unmute yourself, or you could raise your hand. You can also write things in the chat, as is your preference. Well, while we're waiting, I have a couple questions for you. So with respect to Mars, it really struck me in looking at the cross section that you showed that there's not a standout jet stream like there is on Earth. It actually kind of looks as if the jet stream was smooshed up against the polar vortex. And I was curious, what your take on that kind of weird structure that Mars has is.
Yeah, I guess it's a good question. I guess on Earth, those jet streams we associate more with, say, the Hadley circulations and the sort of three-cell structure in the troposphere. And so on Mars, because it's just got that one cell, then I guess it doesn't have that same mechanism for controlling it. And I guess that's why the sort of jet is essentially the polar vortex edge. Yeah, so it would be interesting to see. That's where we think sort of there would be some interesting dynamics on exoplanets, and some of the work that Emily has been showing is showing when these sort of three-cell or multiple cell structures start becoming really interesting, and where the subtropical jets and things like that start separating from those sort of cells.
And what is the mechanism for the dust interaction? Is it changing the radiative processes, or?
Yeah, it is. It's a strange one because in a sense, the polar vortex does act as a barrier to dust. So, so I guess it's hard to see, but we sort of expect that the dust doesn't get inside the polar vortex. So what it's doing is it's changing that temperature gradient across the polar vortex, which allows for a different propagation of the wave dynamics there, but it also just allows for a different sort of I guess potential vorticity gradient. So yeah, that's how it's directly impacting the polar vortex, but also through the Hadley circulation and the strengthening of that, which is very lightly radiatively driven. Unlike on Earth, by the way, when I showed the comparison with Earth, that overturning circulation is very wave driven. So yeah, there are differences there, even when they look very similar.
Cool, thank you.
Hey, Dan, this is Matthew Chinaki. I just wanted to thank you for the presentation. And so I guess I'm curious how the polar vortices, how you see their role in terms of the lower atmosphere and the surface interaction. And just to let you know, I'm an aeolian geomorphologist, so I'm very interested in how that coupling might take place. Is it more long-term climate, or more localized or localized storms? And then the second question would be, have you looked at the Marshall 34 global dust event? Thanks.
Yeah, thanks for the questions, Matthew. So, well, first of all, I'll ask the second part. So we haven't looked at that dust event, but there's more data about to be uploaded to the, I don't know, a lot of the data servers, so the British Atmospheric Data Server. So that Martian reanalysis is just about to include a lot more data, and I'm pretty sure Martian Year 34 is covered in that. So we're really excited to start looking at that. So no, yeah, I haven't.
Grounding in data, for sure. Very well covered. Yeah.
Yeah, so we've not looked at that. I guess in terms of the coupling between the Mars polar vortex and the surface, I think there's a lot of work to be done on the destruction of the polar vortex from the surface polar caps. And one of the things I'm quite keen to do is actually look at modeling those polar caps more sophisticated, using some of the sort of models we use on Earth as well. So there'll be work to be done there. In terms of like the coupling of the polar vortex to that surface, yeah, I don't know actually. I don't know about those more local weather things, but that'd be interesting to look at.
Thank you.
There's a question in the chat from Peter Rhines, which I could read. He says, could you comment on the effect of Venus's very small planetary rotation? A great contrast to other planets with its moving flame-driven thermal zonal circulation.
Yeah, so thanks, Peter. Yeah, so the superrotation on Venus is very significant because of that. I guess less so on, you know, to divert it more to exoplanets. That's one of the things we did feel we could really explore, was that very, very slow rotation rate versus the, well, creating this superrotation. And actually that does seem to create quite strange polar vortices on these exoplanets. And so we do, yeah, I'm not sure how much that plays into the like the chaotic nature of the Venus polar vortex I, but yeah, we're thinking along those lines as well at the moment. So watch this space on that one.